So we've looked at a couple of examples of exponential growth and decay. We kind of looked at the formula and said, oh, okay, this means this means this. Well, I want to get into this pretty heavy because sometimes the equation of the exponential function will be given, as in some of the examples that you did. But other times, we got to be able to derive it. And to derive an exponential equation means that you got to know all the little nuances of this equation so that you can apply to what you're doing right now. What do I mean? Well, generally speaking, let's talk about this. Most of our formulas that you've done so far has been something like this. N t equals to some initial amount. There's the doubling factor, and there's the time that we put it in. Well, here's a couple problems with this. Some things we know, some things we don't know. Yes, we know that this is the total amount. That's why I say A is our total amount, whether we write it as A or whether we write it as A is a function of time. This is our total amount or our final amount. Okay, but what the heck is this symbol? This symbol is actually, with the little zero there, suggests that you're at time 0. Remember that one question where you said you started at 1995 or something like that? Okay, great. You started at 1995, but that was time 0 and you grew from there. See how it works? Perfect. So the 0 here suggests that you're starting at time 0. Okay, perfect. That's why this is the initial amount at time 0. Aha. Now, you know the rest of this. Well, sure, you know B. B is your growth factor, or your decay factor. And you know and I know if B is greater than 1, means that you're growing, you're increasing. But if B is a fraction between 0 and 1, you know that you're decaying, which means you're decreasing. Okay, so this would be like your population growth of your bacteria or whatever. This would be your isotope decay. But what the heck is this? T over P. Well, one of the things that I told you, and I kind of set you up for this in the last couple of questions, where I told you that the growth is this per day, or this per hour, or the decay is this over the number of years, right? But wait a second. What if it doesn't take a full hour to grow? What if it doesn't take a full year to double? So what you have to worry about then is how much time you put it in over how long does it take for it to do this growth or decay. So what does this mean? So this time stands for, this T stands for time, this P stands for period. But what is this? I still don't understand, sir. I don't understand, sir. Okay. Time is your total time. How long are you going to let this experiment run for? Okay? Period means how quickly does it double? How quickly does it go through the cycle? Does it double every 5 hours? Does it double every 15 days? Does it double every year and a half? Every question we've done so far has been doubles every year or every month, or every day, or every hour. Now it's not. This is going to be a period of time that you can say that it doubles in 5 hours. Okay? Well, then that would be 5. The time would be, oh, I'm going to let this experiment run for 20 hours. Guess what? That becomes 20. This thing becomes 20 over 5. It's that simple. Okay, so now I understand that a little bit more. We can apply this. But here's the most important thing about T and P. Okay, when you're talking about the time and the period, they have to be the same units. So if this is in days, that's got to be in days. If this is in hours, that's got to be in hours, and so on. You've got to be careful that those two factors are the same. Let's keep on going. A couple more things we got to talk about. So when we're talking about exponential growth situations, here's the neat thing. Look, if you're doubling, that factor becomes a 2. There's your initial amount. As always, look, initial amount, initial amount, initial amount, no matter what you're doing. Your time allowed to grow over the period for one growth cycle is always T over P, T over P, T over P. And then the only thing that's different is this. Are you doubling? Well, then that's 2. Are you tripling? Well, then that's 3. Are you quadrupling? Then that's 4. Are you halving? Then it's decay. You see how it works? Nice, right? But does that work for everything? Yeah. It even works for something like population growth, or I like this one, money. Yes, money growth. Think about it. The total amount that you get is dependent on how much you invest, and then you're given us something called an interest rate. What is the interest rate? What does the one stand for? What's the I stand for? Well, you don't put an interest rate in. Let's say you get an interest rate of 7%. You got to make sure you convert that to a decimal, 0.07, right? Okay, what does the one mean? The one means 100%. So this means what? This means you get 100% of your investment, which is 1, plus 7% more. So you're actually getting 1 plus 0.07 or 1.07%. That's how much your rate is growing. Because if you got an interest rate of 0.07 and you put it in there, remember, that's between 0 and 1. That means your investment is decaying. No, 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 no. Your investment is growing because it's 100% of your investment plus 7% more. You see it now? Yeah. And then there's your time factor, which we're going to talk about time in terms of something called a period. How often do you actually collect interest? Wow. Let's save that for another podcast, shall we? Let's go right into a question. Okay, so here's our question. The question says a certain culture of bacteria, given suitable conditions, triples. Aha, every 25 hours. So look what that is. There's your growth factor. That's 3. Every 25 hours, that's your period. Ah, I see. The initial count of your sample shows 1,000 bacteria present. So that's your initial. That's your A naught. Aha. Write an exponential function that describes this. Okay, so your total amount, you can write it as A or you can write it as A2 as a function of time. It doesn't matter. Okay, A is the function of time then. Is your initial amount times your doubling, tripling, quadruple, well, triples, okay? Your time over your period, and your period is every 25 hours. So that means that time better be in hours. Be careful. Okay, has to be in hours. So look what happens with question B here. It says approximately how many bacteria will there be in 4 days? Uh-oh, do you see the problem? That was in hours. This is now days. Aha, so convert that. Well, 4 days, you know that you got 24 hours in 1 day, okay? So you multiply that out, obviously, you're going to get 96 hours, right? 4 times 24. 2 times 24, 48 times 2, 96. So how do we do this? Okay. The amount, initial amount. Where's your initial amount? It says you got 1,000 initial amount. So there's 1,000. Triples. 96 hours is the length of your experiment. Your tripling is every 25. That's your period. Look at that. You can just throw this into your calculator now, can't you? So bring up your calculator, and I'm just going to put it in. There's 1,000. Okay. Bracket. There's your tripling to the power of, oh boy, guess what? It's a fraction. So put it in as a fraction. Alpha fraction. There we go. Right? Of 96 hours. And your period is triples every 25. For a total here of 67,943. 67,943. That's how much, that's how many bacteria you're going to have in 4 days. Cool. Okay, now you're probably saying, well, what does this have to do with anything? Well, folks, think about it. Let's say you're a cheese manufacturer, and you're trying to figure out how quickly the cheese cultures are going to actually take that product and make it into real cheese. Now you can start using an exponential formula like this and determine how long it'll take for that cheese to ferment to make actual cheese that you can sell. Huh. Now, here's the next question. How many bacteria are there in 3 days prior to the count? What? Use the same formula. AT A is a function of time. You have 1,000 bacteria. It triples, right, in 3 days prior, which means before you started this 1,000. So obviously there's going to be a whole heck of a lot less. But how much less? Well, think about it. 3 days, you have to still convert into hours, right? Because your period is still based on hours. So 3 days times 24 hours per day works out to be 72 hours, right? It's 72 hours. So, but we're going back. We're going back. Prior means we're going back. So we can actually put in a negative here. Negative 72 hours, right, over the time of 25. Well, that's really, really cool because all you have to do now is just throw that into your calculator. Let's go into our calculator now. Am I going to retype all of this? You know what I can do? I can just go back up here, grab the same formula, bring it here, and just change one number. And the number being, of course, is 96 right up here, right? This is 96 becomes negative 75. Or sorry, 72 because it's 72 hours. Sorry, 3 days, right? If we hit enter now, check it out. I started off with 42 bacteria 3 days before I had the 1,000 bacteria. And see how it works? It's so cool knowing the nuances of the formula. That's the really neat thing that I wanted to teach you.